시린님, 이유가 뭘까요? 원인은 치아 표면의 미세 손상. 그럼 솔루션은 바로 시린매드.
채워주고 감싸주고 보호하니까.
시린은 증상, 매드는 솔루션. 시린이엔 시린매드. 부광약품.
I'm sure you've
Hi, everyone. My name is Soyeon Kang, and today's lecture is Ship Hydrostatics. Today's lecture is quite similar to fluid dynamics. Maybe you already know. Let's get started. This is today's contents. From a point of view of fluid dynamics, all matters consist of only two states, solids and fluids. So a solid can be deformed by an external forces, so it can resist shear stress by static deformation. However, a fluid cannot resist the external forces or shear stress, so it moves or deforms continuously as long as the external forces is applied. For given definition of fluids, there are several classes of fluids: liquids, gases, plasmas, and even plastic solids. We already know and use the terms of density. The density is defined as mass per unit volume and is strongly dependent on temperature and pressure of a fluid. In general, liquid density are about 3 orders of magnitude more dense than gas phases at atmospheric pressure. Pressure is defined as force per unit area. The units are Pascal, bar, psi, ATM, and so on. This is the hydrostatic force in a static fluid, and I will explain about this later. Viscosity is a measure of the resistance of a fluid to flow. So we can move through air easily, but we cannot move through in water or honey. So we call a fluid is thin if the fluid has very low viscosity, and we call a fluid thick if the fluid has very high viscosity. As I explained previously, there are several classes in fluids, but we think the main two states of fluids are liquids and gases. But there are difference in two states due to different cohesive force effects. Generally, density of gases easily varies with applied pressure. However, liquid like water, honey, can be assumed to be incompressible because the density is nearly constant. Therefore, there is little difference in analysis for hydrodynamics and aerodynamics. Here is the pages for pressure in a static flow. In a static fluid, pressure is same at all locations with the same depth independent to the shape of containers. Pressure increases with depth and x always perpendicular to its surface. We can calculate the hydrostatic forces applied to a solid object like this by taking integral of pressure at a given point over surface. And we call this hydrostatic force as buoyancy force. A submerged object like this always experience a net upward force, and this is buoyancy force. The buoyancy force is same to the weight of displaced fluid. The same principle can be applied to calculate the buoyancy on submerged body, both on fully submerged and partially submerged. Iceberg, which has huge submerged volume, also has huge buoyancy force. Submarine can dive into the water and also can float. And this movie is about how submarines dive or float. Sorry.
Just try to click on
Was it?
okay.
That. Sorry.
They can reach depths of about 800 feet thanks to a system of internal and external ballast tanks.
We have 5 external ballast tanks that are normally filled with air when I'm riding on the surface. When it is time for us to dive, we'll open vents on those ballast tanks. There's grates on the bottom of the ship that allow water to come in, displace the air, making the ship just slightly negatively buoyant. We then proceed down to the depth that we want to go to. And we use internal ballast tanks to make the ship neutrally buoyant, that then we can progress on our way in whatever depth we choose.
The crew on board the Virginia class.
Okay. There are 3 states of equilibrium: stable, neutral, and unstable. The only way to know what is the type of stability of our system is to disturb slightly with a slight amount of this body and see whether this body returns to its original position. If so, the system is stable, like this. If the ship is not stable, ship cannot be float in any disturbance, such as wave or wind. So engineers must design the ship stable. If we say the ship is stable, it has to return to its initial upright position if given any disturbance. This is the last movies about ship stability.
You've all seen the videos of cruise ships rolling around. A lot of the time this is down to a failure in one of their systems, the stabilizers. So how do these stabilizers actually work? Let's consider a standard cruise ship. In calm water, she's going to sit happily upright. Her stability is determined by her centre of gravity and her centre of buoyancy. As long as they're all lined up in the correct place, she's going to remain upright and stable. If you then introduce some waves to the sea, she's going to start to interact a bit. Smaller waves are unlikely to have much of an impact on a large ship, but as the wave size increases, the wave length increases, and you're going to start to feel the ship interacting. She's going to roll from side to side, following the rhythm of the wave itself. And this is purely down to the fact that as the water level on one side of the ship rises, the ship generates more buoyancy on that side, and this results in a force that makes her lean over. Most of the time a ship will happily just continue riding the waves, rolling gently from side to side. The only exception of course is synchronous rolling, and that's when the frequency of the wave matches the natural frequency of the ship's roll. This results in rapidly increasing angles of roll until the ship actually capsizes. Apart from that, gentle rolling isn't an issue on most ships, but on a cruise ship, you expect to be able to have a flute of champagne stay put on a table when you put it down. You don't want the ship to be rolling underneath you, spilling your drink everywhere. Instead, these ships use stabilizers to minimize that rolling. We want the ship to remain upright, while the waves run underneath her. The goal of a stabilizer is to counter the force generated by a wave. Unfortunately, that force isn't constant. As the crest of the wave hits one side of the ship, the tipping force is at its maximum. As the wave crest moves through the center line, the force becomes pretty much zero, and then as it moves to the other side, again the force becomes a maximum, but in the other direction. The stabilizer needs to counter all of that. It needs to be able to change the amount of force it generates, depending on the exact location of the wave, which of course is constantly changing. To do that, the industry has come up with a few types of stabilizer. I'm going to split them into two categories, active and passive. A good example of passive stabilizers are bilge keels. These are protrusions on the bilges of a hull, and all they effectively do is dampen any roll. They generate turbulence as they move up and down. To have any effect, they need to apply a force. As they're passive, they can only generate that force when the ship is rolling anyway. Bilge keels are okay at dampening a roll, and they're very cheap to install, so they're a popular design feature on many ships. Unfortunately, they don't do enough to produce the required counter effect that we need on a cruise ship. Another method of
Okay, this is the end of today's lecture. I hope you guys enjoy my lecture, and thank you for your attention.
You question, no question. We can have a break and continue discussion session.